So this is, think of an introduction. This is joint work with Stoller, and it's an overview talk for a paper that appeared in Logic Foundation of Computer Science this year. So logic rules, they're important for design analysis, especially complex modeling, reasoning, analysis problems. And examples are program analysis, networking, including social networking, security, decision support, and so on. And here's a simple rule everybody knows. You give a set of source nodes, a set of edges, you can compute a set of reachable nodes just by these two beautiful rules. But when you have a negation and quantification in the rules, things are much more complex. Many semantics have been proposed, but they're often subtle and they disagree, even on very simple examples. So for example, if you have px, if not px, so is p of Tom true, false, or something else? And if you have px, if px, this doesn't even have negation. Depending on the assumptions, you can get different conclusions. Of course, you have Barber shaves x. If x doesn't shave x, this is Russell's paradox. So we can see for increasingly larger and more complex applications, we must have a unified semantics that people agree was the meaning. So this was what founded semantics and constraint semantics were proposed for. The idea is you want to capture the different assumptions and you want to give really straightforward meaning. Okay, so that was the previous work. We'll see a little bit, but to make it really easy and simple to use and using scale, that's what this work is. We call it design analysis logic. It's based on the unifying founded semantics and constraint semantics. It supports recursive rules with unrestricted negation and arbitrary quantification, and give you the ease and power of programming with different intended semantics. It has really 3 points in this work. You can use meta constraints on predicates to capture different underlying assumptions of these different semantics. And you can use uncertain information in the result of different semantics as either undefined values or possible combinations of values. And finally, you can use knowledge units instantiated with any predicates, including predicates with additional arguments. And just one example, this is the famous win not win example. X is a winning position if you can move from X to Y and Y is not the winning position. It looks very intuitive, but if you have like move 1, 1, so win X if not win X, win 1 if not win 1. So what's the meaning? So if you figure out all the precise logic meaning, you can write inductive definitions like these rules, but they are much more cumbersome with all these quantifications. Indeed, the well-founded semantics, you can just write this one rule and it gives you win equals true, false, undefined. That corresponds to win, lose, and draw beautifully. Except you cannot use the 3 outcomes, in particular, anything that's unknown. After that, everything else depends on it's unknown. Okay, stable model semantics doesn't have unknown. They have a set of 2-value models. For this particular examples, of course, it gave you a sort of no solution. That's not good. So they have different semantic underlying assumptions for good for different uses. So founded semantics and constraint semantics unifies these things by allow you to specify different assumptions. So you can compute the design semantics basically as a least fixed point, give a unique 3-value model. And for the undefined values, you try all combinations as constraint solving, you get a set of 2-value models. Okay, that's a prior work. So the basic idea is for each predicate, you just can say a few things, binary choices, certain or uncertain. It has to be uncertain if you have negation in recursion. Certain means each assertion of P is true or false. So you infer the true, follow the rules, and the rest are false. Uncertain means you can have undefined. So infer true, false, the rest are undefined. Then for certain, you're done. For uncertain predicates, you can say it's complete or not. Complete means all rules with P in the conclusion are given. So you can add completion rules to infer the negation of those P facts using the inverse of the rules about P. And finally, for uncertain and complete predicate, you can say whether it's closed or not. Closed means make an assertion of P false, called self-false, if inferring it to be true requires assuming itself to be true. And you repeatedly doing the infer and add self-false assertions until you reach a fixed point. So you get founded semantics that gave you true, false, undefined, corresponding to conflict, ignorance, or imprecision. And constraint semantics try all combinations to resolve undefined, give you no model, multiple models, or unique models corresponding to these 3. So this work really says, okay, we can capture those with meta constraints, these 4, certain, as we just said. And if you have uncertain but not complete, we call that open. And if you have uncertain, complete, but not closed, we just call that complete. And finally, you have uncertain, complete, and closed, you call it closed. By default, you make it certain if possible, like a move, and that will otherwise make it complete, like a win. And to use the result,
each predicate P, you have 3 separate predicates to capture the true values, the false values, and undefined values. So for example, win.u means the set of positions for which win is undefined. So you can use that as normal predicates. And for constraint semantics, it gives you a set of models called a CS. So for each model in the CS, you can refer to the predicate P by m.p, like m.win. Okay, so that's assumptions and use result. And finally, you can put all the rules together into separate reusable units called knowledge units, okay, and bind the predicates in it to new predicates. And this is just an overview slide to show all these assumptions corresponding well-known previous semantics. So the knowledge unit needs a little bit more. A knowledge unit, you just put a set of rules in a key unit code, give a name, okay, and you can use it by saying in another key unit called win2, you just use that unit, except you bind the move to move2 and win to win2. And additionally, you can actually even have additional argument, not just each of one equals predicates. So this is an example. You use the win unit, but you can pass in additional argument A here. So this is the win rule, except you have an additional argument for each of the atoms in here. Okay, so here's one example that shows when you have both founded semantics and constraint semantics, you can do something like this. So you can use a win unit like before, and here's some game that defines some moves. And this one, compare unit, look at this game and find those that's undefined, okay? But exists a constraint model, and in all constraint models, win is true. So that's, you can actually find such unique positions. So for this example, you have prolog if not ASP, ASP if not prolog, but in either case, you get a move 1, 0. Close means all other moves are false. So in this case, from 0, you cannot move anywhere, so 0 is false. But because move 1, 0 is undefined, so 1 is undefined. But if you use the constraint semantics, you have 2 models. One ASP is true, one prolog is true. But in both cases, move is 1, 0 is true, so win is true. So in this case, unique is true. Okay. So there are detailed semantics and properties and examples in the full paper. This is just a summary slides you've seen. The idea is the 3 things. You can have meta constraints and predicates, just describing these binary choices, and you can use both undefined data and undefined result semantics and combination values, and use the knowledge unit. Okay, and of course, there are a lot of future work to inference and queries. Thank you.